All right, good morning, everybody. In the previous lecture, we were talking about unit testing, right? So in Java, unit testing is basically testing individual constructors and methods, right? You can unit test in a language like C too, where you would unit test individual functions. So when you write a test, essentially you need to call, in Java you would call a method or a constructor, you would call the constructor or method that's being tested. So to call that constructor or method, you need to decide what inputs are you going to use, and you need to decide what are the expected outputs of that method, that constructor or method. Right? So basically, the way this looks is, in Eclipse, right, if you're going to use JUnit to do the testing, the pattern is always similar. Right? So here we're looking at the max2 method that we saw in the first week of the course. Right? To test max2, you're going to first choose some input argument values, right? So what am I going to call max2 with? So I'm going to pick 1 and 100. You're then going to decide, okay, so what is the expected output of the method? So for max2 returns a value. It should return 100, right? The larger of the two values. So that should be, the expected value is equal to y. Right? And now you go ahead and call the method with your chosen inputs. Right? So we call max2, passing in x and y, and you remember what the return value is. And then finally you compare the expected value to the returned value. JUnit's a bit unusual in that the order here matters. Right? So the order here is always expected followed by the value that you are testing. Right? And there's a method here called assert equals. And so when JUnit sees a method that's marked as test, right, it runs the code in the method. And then eventually there will be a statement, or sorry, a line that looks something like this, right? And so there will be a, yeah?
If you can name the variable naming, how do they know that this is an expected versus what you're...
The assert equals method, it says that it's comparing the expected value first and the received, or the actual value second.
No, but how do they know the difference between an expected value versus like another value? Because your expected value is like a variable that you set, but also your got is also...
Yeah, so you have to decide what is the output of, what is the expected output of this method, right? So that's what exp is, right? So if I'm going to use 1 and 100, I know that the maximum of those two values is going to be 100. So I know what the correct answer should be, right? I'm going to test whether or not max2 actually gives me the expected answer, right? And now you're going to compare those two values, right? And so this is the pattern that always occurs in testing, right? Your method or constructor is supposed to do something, right? And so you want to compare what it does to what you expect it ought to do. Right? So if you're for comparing values, you want to test, are those two values equal? And that's what the assert equals method does, right? It compares the expected value to the computed value. If the values differ, then assert equals will cause a failure to occur that JUnit can deal with, right? So let's do this. Let's specify an incorrect expected value. So I'm going to say the expected value is x, which is wrong. Right? So if you run your test case, sure, bloop, bloop, over here, right, you end up with an error. So you end up with a little blue thing, which is failure. Not an error, sorry, you end up with a failure. And down here, it tells you that the expected value was 1, but the value that you're comparing against is 100. Right? And so what has happened here is that thing there has indicated to the JUnit framework that the test has failed. Right? The framework is able to intercept that, or is able to figure that out, and is able to eventually produce an error, not an error message, but a report here to indicate that this is the method that failed, and it gives you some indication of what happened when the method failed. Right? It's simply telling you that the expected value doesn't match the value that was actually returned by the method. So if you correct your test, right, then you end up with a pass, right? So now assert equals runs, the expected value and, well, exp and got are equal. So nothing happens, and JUnit interprets that as a pass. Right? So the test is passed here. Okay, so you can do the same thing. You can do something similar for. Sorry, let me back up a second. So that's testing a static method that returns a value. Right? If you're testing a non-static method, the pattern is similar. You're going to look at the inputs of the method. Right? You're going to determine what is the expected output or what is the method supposed to do, and you're going to compare whether or not what actually happened matches what you expected. So for the advance method in counter, right, so remember advance is supposed to increment the counter by 1. Right? This one's a little bit more complicated. So in this particular case, you first have to make a counter. Right, so you need to make a counter object, and you need to decide what is its state going to be. Right, so we're going to make a counter, C, new counter. Right, so we can start with a counter whose value is 0. Right, so I'm going to call advance, and I expect advance to make the value of the counter equal to 1. Right, so I know what my expected value is. Right, so int expected is going to be 1. Right, call the method. So c.advance. Right, so now I have to do some extra work because now I need to ask the counter what is its value. Right, so this is a little bit different than the previous example where you can just compare the returned value to the expected value. Right, now I need to actually call another counter method to figure out what is its state. Right, so ask the counter for its value. Right, and now I can compare the expected value to the value that we got back from the counter. Right, so again, assert that the expected value is equal to the counter's current value. And if you run that, right, again, hopefully, oh, so this is wrong, right? So here we have an assertion failure, right? So we expected to see the value 1, but we got 2. So something funny is going on. Right? The something funny is going on is because I still have the code that I changed in the previous lecture that shows you the incorrect way of implementing the advance. Right. So let's comment that out, leaving in just the correct version of the method. Right. Go back and rerun your tests. So to rerun your tests, you can rerun them all from over here. So just right-click and run. Or you can run individual tests. So here, if you know this is the one that failed previously, I can simply rerun that one there. And only that method now runs. So if you have a whole bunch of test methods and you want to run one in particular, you can actually pick the one that you want to run. Right? So after fixing our advanced method, we now get a pass. Right? Okay, so let's put the incorrect version back in and comment out the correct version. All right, so that version of advance is incorrect, is correct almost all of the time. It's only incorrect if the value happens to be integer max value, right? And so this particular test here is not going to, it will never determine that there is an error in the method, right? So run that, it's going to pass again, right? And it does, right? So that advance is now passing, the test advance is now passing, right? So why is it not finding the error? Because we're starting with a counter whose value is 0, right? The method only fails if the value of the counter happens to be integer max value. So one of the weaknesses with testing is that you actually have to find the test cases that will reveal your errors, right? If you can't see the source code for advance, right, you have no idea you don't really know what inputs you should be using. You can kind of guess, right? So you can sort of guess that maybe you ought to be testing different values for advance. And if you think about it for a little while, or with experience, I suppose is the better way to put it, you'll realize that, hey, there's this special case that occurs when you hit integer max value. Maybe we ought to test that case. Right? So you stick in another test method, give it another name. So I'm going to test advance, oops, at max value. Right. So I'm going to make a counter now. This time when I make the counter, I'm going to start the counter at integer max value. So fortunately, we have a constructor that can do that for us. Right? So I know that if I advance this counter, I expect to get 0. Right? And if I run our tests again, okay, our first test passed, right, when the counter was 0, but now our second test is failing. Right? So if you can read this, it might be hard to read for you, right? So there we get our assertion error, right? It says that this test expected the value to be 0, but instead we got minus 2 billion something, right? Which is integer min value. And so now you've got your test case that finds the error in our particular method. Right? So now you go back and you say, oh yeah, this is overflowing. Maybe I should fix this somehow. Right? So you go back in this case, I'm just going to put back in the correct version. Right? So you go in, you debug your code, you fix your method, or you hopefully fix your method. You rerun all your tests, right? And now again, we're passing both of our tests. Right? Okay, so the obvious question to ask is, okay, that's great. So I tested 2 counter values. What about all the other ones? Right? And the answer is you probably can't afford to test all of the other possible counter values, right? Which is why there's this quote from back here, right? Testing can be an effective way to show the presence of bugs, but it does not show that your code is correct, right? To show that that method is actually correct, you would have to test every possible counter value. It's feasible to do for the counter. There's only 2 billion possible values. So you could write a loop, test every possible counter value, and test whether or not it returns the correct value. Right? So in this particular case, it's possible to prove that your advanced method is correct. Right? But as soon as your method starts to have more parameters, you run into a problem. Right? So if you try to test a method that has 2 parameters, you now have to test every possible combination of those 2 parameters. Right? If you have 3, you now have to test every possible combination of those 3, and so on and so on and so on. Right? It very, very quickly becomes infeasible to test all input values. And so an important part of testing is learning to figure out what are the good values that you should be using for testing, or what are the values that you should use for testing in order to find the likely errors. Any other examples? So this one, so again, notice this example is slightly different than the previous one. If you're testing a non-static method, generally you have to make an object to call the non-static method, right? With a static method, you can just call the static method you can just call the static method directly, right? So there's no object creation. Again, in a non-static method, often you're testing something about the state of the object, right? So you'll have to call another method to ask the object for some information about itself. And this reveals yet another problem with testing, right? If the value method is buggy for some reason, right? It's probably not, but if the value method is implemented incorrectly, right, your test may now fail, even if advance is correct, right? So if advance is correct, but if value is wrong, well, I still need to use value to actually run this test. And so now you've got this other problem where a test for a particular method may depend on another method, right? And in this case, it's even worse because this test actually depends on that constructor being correct as well, right? And so for all this to work, the class so certain features of the class have to be implemented correctly, right? The constructor has to be correct, value has to be correct. If those 2 things are correct, then I can call advance, and this test method might usefully test the advance method. Right? In a professional environment, the requirement that that be correct and that be correct is not very extreme. Right? The interesting thing about using unit tests to test student code is that the requirement that that be correct and that be correct is sometimes extreme, right? That is, it's very common to see errors in the constructor of a class, right? If there's an error in the constructor, there's almost no way to test any method belonging to that class, right? If the object's never constructed properly, the rest of the methods are probably, any test that you write for the rest of the methods will probably fail. Right, and so finally that introduces yet the other problem, and there's one more problem with testing, right? To write code to test, right, you have to write a test, you have to write code, right? And so now the question is do you test the test? And if you wanted to, how would you do it, right? And that just leads you down this infinite spiral, right? So you have to write code to write testing, to write a test, right? For new programmers, this is a big problem, right? Because if a new programmer is struggling with writing code to begin with, right, writing the test more or less becomes impossible, right? Because if you can't correctly write the test, right, your test will either pass when it shouldn't, or it may fail when it shouldn't, right? And that leads you in all sorts of problems, right? Suddenly you have a test that's failing. You think that the problem actually lies with if you think the problem lies with the method that you're testing, but in fact lies with your test case itself, that can be very hard to debug. Nonetheless, it is very useful in professional software development environments. And it's how your labs are actually tested, right? So the TAs now are currently marking lab 1 with a set of unit tests for all of the methods that you were expected to write. All right, so that's unit testing. So unit testing has led to an entire method of software development called test-driven development. So test-driven development, it's not necessarily its own development method. It's part of many modern development methods. So the idea is that in modern software development, developers rely heavily on automatic testing, right? So that is, in a modern software development environment, what typically happens is you have multiple programmers working on the same project or on the same piece of code, right? Everybody's making changes to that code at the same time. So that code is kept centrally somewhere in a repository of some kind, right? If you've used GitHub at all, that's one of the common central repositories, right? So programmers download the repository onto their computers, and then they upload their changes to the repository. Right? You can set up the repository so that it automatically runs a bunch of unit tests every time someone tries to upload. Right? If the unit tests fail, then the upload fails. Right? And so that prevents people from making changes to the code that don't pass all of the existing unit tests. For this to work, someone has to write the unit tests. Right? And so this leads to this whole process called test-driven development. So you decide that you need to write some software. Before you write any of that software, you actually write the test code first. It doesn't have to be complete test code, right? You can just write some very quick and dirty test code for the class that you want to create, right? Then you write your code and you run the tests, right? You make sure that the tests pass before you continue, right? So you run all the existing tests and see if any of the tests fail, right? Sorry, write the code, right. Run your test. If any test code fails, you fix your code and you repeat, right? And so you go back to step 1. So you go to write another method. When you write your other method, you write a new test case first, right? Then you write your code, you run your tests, right? Repeat, right? Making sure that all of your tests pass before you do make any progress. That part's actually pretty important, right? So if you're writing code and tests are failing and you keep on adding new code, it becomes very, very difficult to find out where is the error in your code. And it's a common mistake students will make, right? So if I give students a bunch of unit tests to help them develop their source code, what a lot of students will do is they'll just start writing code. And then at the end, they'll run all their tests, and then every test will fail, and they'll have no idea where the error has occurred. And so this process it's actually fairly important that you follow the steps in this process, right? Write a test, write the method, make sure the test passes, then proceed. All right, so that's all I want to talk about regarding testing. Any questions on testing? Okay, moving right along. So we're actually going to go a bit backwards at this point. We're going to talk about static stuff inside of a class. So that's where we started in the course, right? So in the course when we started out with a class. Everything in the class was static, right? So I now want to revisit that. So you've seen that you can have methods that are static, right? Because all of our classes had static methods to begin with. You can also have fields that are static as well. Right? And so static features, so fields and methods, they are associated with the class instead of being associated with the individual objects. Right? That is, if you want to use a static method or a static field, you use the name of the class instead of an object to access them. Right? A static field is a field, so it's a variable, right? That's static. Right? The fact that it's static means it belongs to the class and it doesn't belong to any particular object. What that means is that there's only one copy of the field. Right? So remember, for non-static fields, every object gets their own copy of that field. For static fields, the individual objects do not get a copy of that field. Right? So every object that's created using the class ends up sharing the exact same copy of the field. Right? So these things are called class variables to indicate, Java normally uses the term static field. Other object-oriented programming languages will call these class variables or something like that, right? As opposed to instance variables, right? So a class variable belongs to the class. Instance variables belong to individual objects. So this is a little silly example that I have in SISC 124 to illustrate the use of a static field, right? There's a little class called domino that was created for 124. It just represents one of these domino tiles. Right? If you don't know what a domino is, it's a family of games that you can play with these tiles. Right? The tiles have two sides, and they have they're marked with a number, or pips, I guess, is what they're correctly called. Right? And so in a standard set of dominoes, you can have a side that has a value of 0, and the maximum value is 6. Right? And that's just showing you the standard set of dominoes there. Right? So if you wanted to make a class that represents a domino, it's pretty straightforward. Right? Every domino has two sides, so it has it has two values, which I'm calling value 1 and value 2. Right? It might be useful to know what the minimum value is for a side of a domino. So I've got a field called min value, that's static, right? And I've got a field called max value, that's static. Right? Why are they static? Because it doesn't make sense for every domino to have its own minimum and maximum value. Right? The minimum and maximum value is the same for every domino. I only need one copy. So it makes sense in this case to use a static variable to hold those values. Value 1 and value 2 cannot be static. Right? If they were static, then every domino would have the same two sides. Right? So they have to be non-static so that every domino can have its own independent number side. Yep. Final means you can only assign this variable a value once. Right? So if you say min value equals 0, there's your assignment once. You can't do it again. If you try to do it again, the compiler will flag that as an error. Right? So that looks a lot like a const int in C. Right? Whoops, sorry. Boop, boop. Right, so if you were to draw the memory diagram for this thing, right, when you make a domino, so this code here makes two dominoes. There's the domino class there, right? Now remember, to make the first domino, you copy the class and you plunk it down here. Right? To make the second domino, you copy the class and plunk it down there. Right? I guess I should have shown value 1 and value 2 in the class. Anyway, when you copy the class, you don't copy the static fields. Right? The static fields stay with the class. Right? So that domino object and that domino object, they don't have their own fields of min value and max value. Right? The static fields belong to the class. Right? The non-static fields belong to the objects. When you're accessing anything that's static, you always use the name of the class. Right? So if I want to access min value, I write domino.minValue. Right? So that's we've done that before. Right? In math class, if you want pi or e, it's math.pi and math.e. Right? So pi and e are both static fields in the math class. Now, unfortunately, when Java was created, the designers decided that it would be legal to access a static field using an object. Right? So you can make a domino object here. Right? Notice the previous example, there's no object that was ever created. Right? Now here, I'm making a domino object, and then I'm going to access min value using the object. Right? So this is legal in Java, but it's considered bad form. Right? So this is something you're not supposed to do. They really should not have made this legal. But anyway, it is. So unfortunately, you can write that. Sorry. Oh, sorry. Right. So unfortunately, you can write that there, and that will compile and run. Right. So we'll give you the right value. Avoid doing that. Right. So a final field is only assignable once. So it's not just fields. You can also create final variables. Right. So you make a local variable, mark it final. You're only allowed to give it a value once. If your class has a public static final field, then basically your class is saying, hey, look, I've got this constant here that I want everybody to know about. Right? So for the dominoes, it kind of makes sense to advertise the fact that the minimum value for dominoes is 0 and the maximum value is 6. Right? For the math class, it makes sense to tell everybody that pi is 3.1415, blah, 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 blah. Right? If you create a static final field, then you're probably going to give it a value where you declare it. You don't have to. Right? You have to give it a value somewhere. It doesn't have to be here. Right? When you give it a value, you can only do it once. So if you try to assign to the same value twice, that won't work. Right? So public static final fields, they're meant to be constant values that are a meaningful part of the idea that you're trying to convey with your class. Now, this keyword final really confuses a lot of new Java programmers. So I have to go through some examples here. If you have a primitive type field and you mark it as final, then that thing there really is constant. Right? There's no way for you to change min value because you've given it a value here. Right? If you try to write domino min value equals something anywhere else, right, even inside the domino class itself, the compiler will flag that as an error. Right? It'll say you've given it a value once and it's final. Right, you can't reassign. So final primitive value, it's basically a constant. If you have an immutable type, that's not a primitive, right? So an immutable class type, immutable reference type, then the string object in this case is effectively a constant as well. So here I've got a static final string called x, right? It's set to the string peekaboo. Right? If you try to, so first of all, you can't change the state of that string. Right? There's no way for you to change the characters in peekaboo. So the string itself is constant. But I also can't reassign to x. Right? So if I try to write nothing to hide.x equals something else, that won't compile. Right? The compiler will tell you, hey, you've already assigned a value to x. You can't do it again. Right? So if you have an immutable type, then it's effectively constant as well. The problem comes when you try to make a final static field that's not immutable. So something like a list. Right? So here I've got a list called empty. Right? Presumably, right, anybody looking at this code is going to say, well, okay, this thing empty is always the empty list. Right? The problem is it's not. Right? So this looks like it's a constant empty list, but you can use the name empty because it's public, right? And you can call any method you want on it. So you can call add, right? And add a string to the empty list. So your empty list is no longer empty, right? So if you have a mutable type, it's not really a constant, right? So you should avoid using mutable types as public constants. They're not logically constant, right? So the thing that's constant here is the reference, right? Empty always refers to that list, right? But the list itself is not necessarily always empty, right? You can change the state of the list, so it's not logically constant. Okay, so what about static methods? So a method that's static, question?
Is there a prefix that makes it feel?
Sorry, someone just came out of the other, is there a
Is there a prefix that you can make mutable types?
No, there's no way to do that. So if you have a mutable type, there's no modifier that you can use to take away the mutability of the type. The best thing that you can do is wrap that type inside of another class and override replace all of the methods that change the state of the object so that they do nothing or something like that. But there's no simple way to disable the mutability. Okay, so static methods are methods that belong to the class. You always use the name of the class to call the method. Right? So like variables, these are also called class methods. Right? So to emphasize the fact that the method belongs to the class. Right? So inside that domino class, you might stick in a static method that checks whether or not some given value is a legal domino value. Right? Why is it static? Because every domino object doesn't need its own version of isValue OK. Right? The method is never going to look at the two sides of the domino. Right? It's only going to look at the static fields min value and max value. Right? So if you have a method that's only using the static stuff of your class, you can make the method a static variable as well. You can make the method a static method as well. Right? If your method needs to access the non-static fields of the object that was used to call the method, then it can't be static. Right? This one can be static because we never look at the two sides of a domino. So when you use a static method, it's always the name of the class that's used to call the method. Right? But just like with fields, the language designers decided that it would be OK to call a static method with an object reference. Right? Again, they should not have allowed that. But we're stuck with it now. Right? So avoid doing that. Right? The problem with doing this is that if someone comes along and reads this code without looking at how isValue OK is actually defined, they're going to think that this is a non-static method, right? Because you're using an object to call the method. All right, so we're really going backwards now. So at the beginning of the course, everything was static, right? We had classes that just had a bunch of static methods, right? It turns out this is the most uncommon type of class that you would create in Java, right? So these things are called utility classes. Unfortunately, they look exactly like your C programs that you would have written in your previous courses. Right? So a class is supposed to be a model of a thing or concept, right? Normally, classes in Java are used to create objects. So the class is used as a blueprint to generate new objects. Right? Every once in a while, so very occasionally, it's useful to create a class that is not used to make objects. Right? So in other words, it's useful to make a class that doesn't have a constructor. Right? These things are called utility classes. Right? So these classes have no constructor. Therefore, you can't make objects of that type. Right? Everything in these classes is marked as being static. Right? If it has fields, they're all static. All of the methods are static. All of the features in the class will be marked as being static. Right? So you always use the name of the class to access the features of the class. Right? The standard library is very large. It only has a handful of these classes. Right? So math is one of these classes, arrays is one of these classes, and collections is one of these classes. Right? There aren't very many utility classes in the standard library. So you might ask, why would you want to make one of these things? And so the idea is that you can create a utility class, and that groups together a bunch of related fields and methods, right? Which is what every class does. Right? But with the addition that making objects is never necessary. Right? So the math class groups together mathematical constants and functions. Right? I don't have to make a math object to compute the cosine of a number. Right? Similarly, collections groups together a bunch of methods that operate on Java collections, so basically lists and sets. Right? If I wanted to sort a list, right, I don't actually need to make some collections object that can then sort a list, right? I can just write a method that knows how to sort a list, but I don't need to make an object that can sort another list object. Right? So utility classes are never used to make objects. Right? When you use a utility class, only the class itself occupies any memory. Right? So to compute the cosine of an angle, I just write class name dot cosine. Right? To compute the sine of an angle, I just write class name dot sine. Right? You never make a math object. Right? Therefore, I don't need to spend any memory making math objects just so that I can call cosine or sine. Right? If you were to look at what the memory diagram looks like for this, the math class sits in memory somewhere. Right? It's got a field called pi. It's got a field called e. Right? You never make a math object to call cosine or sine. Right? So when you call cosine and sine, the math class, you go to the math class, you find its sine method or its cosine method, and that method runs. Right? There's no object that needs to be made. So making a utility class is very easy. Right? You just make a class, you mark everything as being static. Right? So as a simple example, we're going to make a little utility class that basically computes E equals mc squared, right? So Einstein's mass energy equivalence equation. Right? So how do you do it? It's very easy, right? Make a class, give it a name. Okay, so it's easy. Step 2, put in whatever constants you need. Right? Make them all make them all static and final. Right? If they're useful to people using, if they're useful for people using the class, mark them as public. Sorry. Okay, so when you make a public static final field, or when you make a final field, the convention is to write the name of the field in all capitals, right? And that's to indicate that it's a constant of some kind, right? So here it's, C, right? Integer, min value, and max value. It's all caps min value, all caps max value. There is stick in your methods, right? So all your methods will be static. If you want people to use them, make them public, right? And then inside the method, if you want to, you can use the static field. That's no problem, right? So I can write relativity.c, or just plain old C here, if you don't want to type in relativity, right? So mass. So E equals mc squared, right? And return that value. And that's it, right? Everything's static. It's pretty straightforward. There's no constructors yet, right? So if you want to use the class, you're always, if you want to use the class to compute, to call that method, if you want to use that method, you use the class name to call the method, right? So you don't make a relativity object. You just call the method using the class name, right? And if you run that little program there, so that's 1 gram of mass. 1? Yes, that's 1 gram, right? Generates that much energy, right? So 9 times 10 to the 13, which is a huge amount of energy, right? That's about the amount of energy that was released by the first atomic bomb that was dropped on Japan, right? So that's just 1 gram. So if you can convert 1 gram of mass into energy, that produces a lot of energy, right? Nuclear power plants are useful in that regard. Okay, so our class doesn't have a constructor. There's nothing in it, right? There's a field, there's a method, that's it, right? But remember what I told you when we were talking about constructors, right? If you don't create, if your class has no constructors, the compiler sticks one in for you, right? So you can actually write that, and our class as it stands will compile and run just fine. So you can, in fact, make a relativity object. So if you don't define any constructors, you get one for free, right? So the one that you get for free in this case basically does nothing, right? There's no non-static fields, so there's nothing to do inside the constructor. It's not 100% true, but for our purposes right now, it does absolutely nothing, right? Okay, so that's unfortunate, right? It's not the end of the world. But it would be nice if we could stop that from happening, right? So if you decide that you want to make a utility class, you should really stop people from calling it a constructor, right? If they try to call the constructor, that should not work, right? So you can do this, right? The way you do this is you simply create a private constructor, right? By making it private, nobody outside the class can call the constructor. By adding a constructor to the class, that stops the compiler from putting in the public no argument one for you, right? So the trick is make a private constructor. It doesn't matter. It can be any constructor, right? It doesn't have to be the no argument constructor, right? It's typically empty by design. And now, if somebody tries to write new relativity, the compiler will say there's no publicly accessible constructor. Right? So if you decide to make a utility class, or if someone asks you about this on a test, right, make sure you have a private empty no argument constructor, or some constructor. It doesn't have to be the no argument one, right? Make sure there's a private constructor, and that'll stop the compiler from generating the public one for you. Right? So static classes where everything is static, they're called utility classes. They're super easy to make, very occasionally useful, but uncommon in Java. More common, though, or very common, I'll say, in Java are these things called static factory methods. Okay, so static methods and fields. So fields are somewhat uncommon in Java. Static fields in Java are somewhat uncommon, right? It's not very often that you have a constant in a class that you want everybody to know about. I mean, you see them, but they're not super common, right? They're not the most common example of a field. Classes where everything is static are very uncommon. However, static methods in a class are quite common, right? And probably the most common kind of static method in a class are these things called factory methods, right? So remember, Java classes are meant to make objects. A static factory method is a static method that makes an object. Right? That's why it's called a factory method, right? It makes and returns a new object. Okay, so you can use these things to create methods that behave essentially like a constructor, right? So remember, what does a constructor do? Well, it initializes a newly created object, right? Factory method returns a new object, right? So a factory method creates and returns a reference to a new object, right? Now, the reason why these are so useful is because constructors, their names are always the same as the name of the class. But if you have a method, you can give it whatever name you want. So now you can make methods that have their own names that more or less behave like a constructor, right? So remember our point2 class? Right, it's got a constructor that takes in an x and a y coordinate. Right? In your calculus course in first year, you should have been told about the polar form of a point. Right? So the polar form of a point is just the point where it's defined by the angle measured relative to the x-axis and the distance of that point from the origin. Right? So the coordinates of that point is just r cos theta, r sine theta. If you're making the point2 class and you decide, hey, I want people to make a point given its polar form, right, given r and theta, right, you might at first stick in a constructor that takes in a radius and an angle as two double values, right? And as soon as you do that, you'll run into a problem because the existing constructor has the exact same signature as your new constructor, right? So that's an illegal overload, right? Both constructors have the same name, right? If you really want to put in a constructor that looks like this, the trick is make a static method that returns a new point given its polar form, right? So get rid of the illegal overload by providing a static factory method, right? You'll also occasionally see this. So it's called the named constructor idiom, right? So named constructor because it behaves like a constructor. Right? So how do you do this? Well, it's easy. You make a static method, right? It returns an object, You give it a name, so I'm just going to call this polar, right? And you pass it, then you have your arguments, right? Or your parameters, sorry, right? The implementation is pretty straightforward, right? The x coordinate of the point is just r times cos theta, right? The y coordinate of the point is just r times sine theta, right? Now I need to make and return an object. So here's where I call the constructor for point 2, right? To make a point 2 object, and I make the object passing in our computed values of x and y, right? So now someone's got a method that returns a new point given its polar representation, right? And that prevents the problem of having an illegal overload. It's also, right, very easy to read this method and understand or guess at what it's going to do, right? Just looking at the name of this method, you can guess that it's going to return a point equal to, given its polar form, right? So if you look in, if you would actually look in the point 2 class at the source code, you'll see that there's a whole bunch of factory methods, right? So, well, let's go ahead and look. So I never showed you the vector 2 class, but there's a companion class to point 2 called vector 2. So a point represents a point in space. A vector represents a mathematical vector, right? Probably in your first year calculus and physics and calculus courses, you were told a point is just a vector. That's not really true. A point is a point. A vector is a vector. It just so happens to be the case that you can often treat the two things as the same thing, right? So the point 2 class and the vector 2 class work together. I can take a point, add a vector to it, and that produces a new point. So somewhere there's an add method. I just have to scroll through and find it. There it is. So here's our add method, right? It's non-static, right? So I can add a vector to a point, and that moves the point, right? So p dot add v moves p so that its new coordinates are the original coordinates of the point plus the vector v. Right? Let me close this thing over here. Okay. So that version of the method, there's a useful comment up here, right? So use this method when you want to write something like, p equals p plus v, right? So I want to add a vector to a point and actually change the coordinates of the point, right? Now, if you look at the source code, you'll find that there's a static version of this method as well. Where'd it go? Somewhere there's a static version of add. Here. Okay, so now there's a static version of add as well, right? Now it's static, so you're not going to write p dot add, right? You're going to write point 2 dot add, and now you're going to tell it the point and the vector that you want to add together, right? And so that's the sort of thing that a C programmer would write, right? Write an add function that adds a point and a vector together, right? The object-oriented, or the object-oriented version of the object-oriented version of that method is the non-static version. Where'd it go? I should have put these together. Sorry. Is the non-static version, right? So in Java, you write p dot add and then v, right? But you can provide both of them. You can provide both versions of the method, right? The name is add, but the parameter lists are different. So we can have both methods in the class at the same time, right? This version of add returns a new point that's equal to p plus v, right? So it doesn't change the coordinates of p. It uses p and v, adds them together, and gives you back a new point, but it doesn't change p, right? How does it work? It's a static factory method, right? So you make a new point, right? You compute the coordinates of the new point by adding the coordinates of p and v, right? So I'm going to go and get the x coordinate of p. I'm going to get the x component of v, right, and add those together. So this is subtle but important point, right? I can write p dot x to get the x field of p directly, right? So I'm inside of a static method. I'm inside the class point 2. Right? Because I'm inside the class point 2, I'm allowed to look at the static fields, all of the fields of a point 2 object, even if they're private. Right? So I can legally write p dot x here to get the x coordinates of the point. Right? even though I'm inside a static method. Right? I'm not in the vector2 class. Right? So I can't look at the private fields of vector2 directly. So to get the x coordinate of the vector, I have to call the vector's x method so that I can get its x component. Right? And the same is true with y. Right? Am I late? Am I overtime? Oh, I am, sorry. Right? So the same is true with y. Right? I can access the field y belonging to P directly because I'm inside the point 2 class, but I can't do that with V. Right? I have to call the method instead. All right, I guess we'll call it quits there and finish this off in the next lecture.